I've got a nice advanced calculus problem to show you today, and this comes from a cool blog that I just stumbled upon called Calculus Plus Epsilon. So take a look at this blog if you'd like to. There are lots of nice results and problems. Okay, so our goal is to show that if f is continuous, then the limit as y goes to infinity of y times the integral from 0 to 1 of x to the y times f of x dx is equal to f of 1. And really what we need is f to be continuous on the interval 0 to 1. But I'll just leave continuous kind of in a broader sense there because it's easier to write down. Okay. What I think is pretty cool about this is like you've got this limit and integral kind of combination that pulls out a value of a function. And this feels pretty similar to the Dirac distribution or the delta function that you sometimes see in like a physics class or sometimes at the end of a differential equations class. That also like essentially combines a limit and an integral together to give you a value of a function. And then maybe if you want to think about this follow-up when you're done, I think maybe there's a simpler argument if you assume that f is differentiable instead of just continuous. Okay, so anyway, let's get to it. Okay, so we're going to start by letting epsilon be bigger than 0. And what we'll do is bound the difference of the left-hand side and the right-hand side below epsilon. But because epsilon was chosen arbitrarily, then the difference must be equal to 0. Okay, so that's good. But if we're using an epsilon, then that means we probably want to use maybe this continuity to come up with some delta. And that's exactly what we're going to do. So given some arbitrary epsilon bigger than 0, let's take a delta. And we're going to take a delta between 0 and the number 1 over e. You'll see why we choose 1 over e. It kind of makes the calculation nice, such that if the absolute value of x minus 1 is less than delta, then the absolute value of f of x minus f of 1 is less than epsilon. So that's by the continuity of f at the number 1. And I guess I should say the traditional way to do this with a couple of more words is to take a delta 1 maybe, and then choose your final delta to be the minimum of that delta 1 and the number 1 over e. That's just if you want to like constrain the original value of delta a little bit to begin with, but we can do it this way. I think this is fine. Okay, so this is looking good. But let's notice if x minus 1 is less than delta, then that means that for all x on the interval from delta to 1, we have this inequality is satisfied. Even though by the definition of continuity, we have this stronger result for our setup, since we're working with this integral from 0 to 1, this is all that we're going to need. Okay, so now let's take the absolute value of the difference of this left-hand side and this right-hand side. So that's going to be the absolute value of the limit as y goes to infinity of y times the integral from 0 to 1 of x to the y times f of x dx minus f of 1. Okay, and this is the thing that we want to show is less than epsilon. But I'm going to do a bit of a trick here. Notice that this f of 1 is really outside of this limit because it's coming from the other side of this equation. I'm going to bring it inside the limit by multiplying by something whose limit is 1. And the version of 1 that I'll take is y over y plus 1. And then let's maybe put some parentheses here just to show that that's all within the limit. Okay, and now from here, I'm going to take this thing, which is written as y over y plus 1, and then express it similar to what we have right here. So as an integral from 0 to 1 of f of x. So notice I can do that without much trouble. That's the same thing as y over y plus 1 times f of 1, and then we're evaluating that from x equals 0 up to x equals 1. Okay, so we're thinking about that like a zeroth integral where we're evaluating at the two endpoints. Now from here, what we'll do is take the derivative with respect to x and turn that into a single integral. Notice taking the derivative with respect to x will leave us with y, and then the integral from 0 to 1 of x to the y times f of 1 dx. Okay, great. But now we see that we've got this integral from 0 to 1 of a function of x dx, and then an integral from 0 to 1 of a function of x dx. So that means that we can combine those two things together. So in fact, what we have is the absolute value of the limit as y goes to 0 of y times the integral from 0 to 1 of x to the y, and then f of x minus f of 1 dx. Okay, so that's where we are. And now from here, I'm going to bring these absolute values inside the integral using an inequality. It's essentially the triangle inequality for integrals. And I'm also going to split this integral from 0 to 1 into pieces. So that's going to give me an inequality. This is going to be less than or equal to the limit as y goes to infinity of y times, let's see, we'll have the integral from 0 to delta of x to the y times the absolute value of f of x minus f of 1 dx, where that delta is this delta that we have up here, chosen so that our difference is less than epsilon, and then plus the integral from delta up to 1 of x to the y, and then the absolute value of f of x minus f of 1 dx. And then maybe this is all in parentheses right here. Okay, so just to reiterate, the difference between the left-hand side and the right-hand side of this boxed red thing has been shown to be less than or equal to this expansion. Okay, so now let's maybe bring that up and then we'll finish it off. So this is where we left ourselves off. So I rewrote this a little bit. I took the difference of both sides of this equality, and we showed that that was less than or equal to this object right here. Now we're ready to work on this a little bit. So notice by our assumption up here, since when x is between delta and 1, we have absolute value of f of x minus f of 1 is less than epsilon. We know that here, this means that this object is less than epsilon. Okay, so that's a good thing to see. So that's a good place to be. And now we can use the fact that this difference is a continuous function itself. That's because we have a continuous function and we're like subtracting a constant. So this is an obvious continuous function. And then it's continuous on this bounded domain from 0 to delta. So that means it achieves its maximum somewhere. So that means we can say all of this is between 0. So let's maybe just bring this down to a box. And this box is between 0 and some number m. And that's going to be for all x on the interval 0 to delta. Again, that's by the extreme value theorem. So that allows us to do a bit of simplification. So let's see what we have now. So our whole thing is less than or equal to, again, we have the limit as y goes to infinity. And then we'll have y times, so we'll have m times the integral from 0 to delta of x to the y dx from this first one. And then from this second one, we'll have plus, and I'm going to do a bit of a trick here. I'll bring the epsilon out, and then I'll have the integral from 0 to 1 of x to the y dx. So I replaced that delta with a 0, but that's just going to have the effect of pushing our inequality further in the correct direction. And now let's see where we can go from here. So this integral from 0 to 1 of x to the y, that's pretty easy to calculate. That's just y over y plus 1. And then we can do a further inequality on this one. Replace x with its largest value from this interval. That's because x to the y is an increasing function when y is kind of large enough. I think that's pretty easy to see. So we can replace this with delta to the y as long as we put an inequality there. Okay, then that delta to the y is being integrated between 0 and delta, so that gives us a multiple of delta out front. And then finally, we know that delta is less than 1 over e, so we can use that in our inequality as well. So this whole thing is less than the limit as y goes to infinity of y times delta times 1 over e to the y from this thing right here, and then plus epsilon times y over y plus 1. So we're left with that sort of limit. Notice delta is just a constant. Then we have y, which is a polynomial, over e to the y, which is an exponential function. Whenever you're taking a limit as y goes to infinity, the exponential function always wins. So that means this whole thing is going to trend off towards 0. Then here we've got y over y plus 1. That's a rational function. That clearly goes to the number 1 just by using standard tricks for limits of rational functions. So we're left with 0 plus epsilon. So this whole limit is epsilon. But since epsilon was chosen arbitrarily, and we showed that the difference of these two things is always less than epsilon, that means that these two objects have to be equal, which was our original goal. And that's a good place to stop.